Okay, when's our exam?
The 31st.
Yes. Where's the material start? I'm just going to start with the voltage difference. Going to go up to all the RC circuits, the resistors, capacitors, all the stuff we're going to do now. So basically, it's going to do the RC circuits, AC circuit stuff. That type of stuff there. So what we want to do today is we want to look at capacitors in series and in parallel. And we started this last time. We're looking at capacitors in parallel. So we have this here, and one capacitor, another one, and this is. What did we say we wanted to do with that mess? We want to replace this mess with one that's equivalent to these here. So we want to take this and replace it with this. So this is going to be equivalent to all these here. And so what did we say about this case here? We said that this capacitor here has a charge of Q1. This capacitor here has a charge of Q2. This capacitor here has a charge of Q3. And if this capacitor is truly equivalent to this over here, what did we say? What has to be its charge? If it's truly equivalent.
Q1 plus the 2 plus the 4.
Put the Q's in there. Okay. So, because what happens here, in order for this to have a charge Q1, what would have to happen? Well, you'd have to have Q1 electrons basically move through here like this. That'd have a charge of Q1. But then you'd also have to have Q2 electrons going this way, and then Q3 electrons. So what's the total charge going through here? The Q1, Q2, and Q3. So this Q total over here would have to be the sum of these ones here. Am I going off? So I'm going to up it over here. So this Q total has to be Q1 plus Q2 plus Q3 to make it equivalent. Okay, once we have that, everything else will send pretty slow. So we have this right here. Now, what's the voltage? Well, what's the definition of capacitance? We said that C is by definition Q over this magnitude of delta V. I told you we're going to do something here. What did I say we're going to do with that magnitude of delta V? We're just going to replace it with a simple V. So we're not going to write it like this anymore. We're just going to start writing this as C equals Q over V. And so what this means here is that the charge on something equals C times V. What do you have for a resistor? For a resistor, the voltage is IR. So different elements are going to have different voltages across them. Resistor is always IR. Capacitor is always is going to be the Q over V as your C. And so your voltage in this case, if you solve for the V, would be Q over C. Okay. So what do we have here? What would have to be then the charge on this guy here? From that relationship. The charge on this one would have to be, right? If I put a voltmeter across here, this would read V1. If I put a voltmeter across here, this would read V2. If I put a voltmeter across here, that one would read V3. So what would you put in for Q1? This would be C1 V1. What did you put in for Q2? I see a pattern. Yeah, C2 V2, and then we'll finish it off with C2, C3 V3. Now, what can I then say about the total charge over here? This is V. What would have to be the total charge here then? This is CEQ. This would have to be CEQ times voltage V. Now, what do you know about anything in parallel? Anything in parallel always has the same voltage that's here. So what we have here is that the V1, we know that V1 equals V2 equals V3 equals V. Because we're in parallel. So all those V's cancel. So this just tells me the equivalent capacitance is C1 plus C2 plus C3, 4 capacitors. In parallel. Okay. Now what's going to be tricky here? When you have resistors, when I say the equivalent of resistance is R1 plus R2 plus R3, those resistors are in series. They're in series, so they get flipped. And that's going to be a lot easier to mess up than you think. Okay, so this is what you have for capacitors in parallel. You have resistors in series, and you have the equivalent thing. So the expression is going to be flipped. That make sense? Okay, let's do the case with series capacitors. There are you examples. Okay, with any luck, the weather is supposed to drop down to normal temperatures, I think, starting tomorrow. So with any luck, we'll be in our old room tomorrow. Ivy? Yes. Okay. Okay, so now let's repeat for capacitors in series. Okay, so we're going to have a battery here. And I have a capacitor here, C1. And another one here, C2. Another one here, C3. Hey, what do we want to do with that mess? Replace it with one capacitor that's equivalent to these here. And there's going to be there's a subtle point here. So let's go through and do this. Now, let's go through the subtle point here. And to make this wire kind of thick here like this. So John thick wire here, there's a reason why. What do we say a battery is? What's important about a battery? It is the electric field. Okay. So a battery is going to be whenever you have a voltage difference, it means you have a source of an electric field. And you need that because that's going to make charge move. So we're going to have an electric field like this. Here. And like that. Okay. So here's the tricky part. If you're in a little electron here, what happens to you? Yeah, you come over here and then you hop over to here. What's going to happen? More charge is going to go this way, and then more charge will go this way, then more charge will go this way. So this little top plate is going to get a charge of plus Q. What about this bottom plate here? Minus Q. Now here's the subtle point. If you look at this section right here. Okay. What is the net charge for this entire region here? 0. Well, if I have a plus Q charge here, what do you think that plus Q charge is going to do? And there's going to be some electric field coming out. It's going to actually attract electrons going up toward it like this. So what's going to happen here is that this little charge here, this plus Q here, is going to attract. It's going to attract a minus Q charge here. Well, this is electrically neutral, then what is going to be the charge here? Plus Q. Hey, what do you think this little section here is going to do? What's this charge initially? 0. Hey, well, what is this going to do here? Yeah, this is gonna attract a negative Q here. And this is gonna then have to be positive Q because it's electrically neutral. So when you have capacitors in series, what do you know about the charges? They're all the same. So for capacitors in series, the charge is the same. Okay. Now, how much charge has been pumped through this battery here? Has there been 3Q of charge pumped through this battery? I want to figure out what has to be the charge over here. So remember the last time when we had the capacitors in parallel, what happened? Well, this had a charge Q1, this had a charge Q2, this had a charge Q3. So the Q1 charge got pumped through the battery. So that was Q1 that went through the battery. Then the Q2, well, we had Q2 going through the battery. So there was Q1 and Q2 going through the battery. Then Q3 went through the battery. So the total charge going through that battery was Q1 plus Q2 plus Q3. In this case here, how much charge has been pumped through this battery? Just Q, right? So what happened here is we had the charge here go through like this, more charge, eventually this became plus Q, this became minus Q, then the other charges were just from the separation of how the charges worked. Okay, so the only charge being pumped through here has been Q. So if this is truly equivalent to this has to have a charge of plus Q, this has to be minus Q. If it's truly equivalent. So this already tells us something. If you want to store a lot of charge, and you have capacitors, how would you connect your capacitors if you want to store a lot of charge? You want to put them in parallel. So if you put them in series, you're not going to get a lot of charge. So if you need to store a lot of charge, you have to put those capacitors in parallel. Okay. Well, you're a pro at this. You tell me what to do. What do we know about anything in series? For anything in series. Yeah, the voltages always add. So this voltage here, if this has a voltage here, if I put a voltmeter here, this has a voltage V1. If I put a voltmeter here, this has a voltage V2. If I put a voltmeter here, this has a voltage V3. The total voltage here has to be this voltage plus this plus this. So for series. We have to say V equals V1 plus V2 plus V3. Okay. Now, what's the voltage of a capacitor given by? Remember, we have our definition of C. Our C is by definition Q over V. So what's the voltage of a capacitor?
Over C.
Yeah, we take our V and our C, we flip them. This gives us V equals Q over C. So this has to be what? This has to be the charge on that first capacitor, which is Q, over C1. Hey, what's going to be the voltage on the second capacitor?
Q over C.
Yeah, charge, okay, which happens to be the same, over C2. And then likewise for this one, this is Q, over C3. Hey, but what's going to be the voltage on this guy over here? Yeah, Q over CQ. Hey, what crazy thing happens? All those Q's cancel. And that gives me this. That makes sense? Again, what's going to be hard here? What does that expression look like? With the resistors, this looks like parallel. The resistors in parallel. But this is what happens when you have capacitors in series. So again, those equations get flipped. So that's just, and you think, well, yeah, that's kind of an obvious point. Not when you're on a test, because you're on a test, you get nervous, and then you don't think it's clear because you're nervous, and then you can easily get these things screwed up. Okay. Okay, that's all you need to know this. For that, let's just do an example, see how it works. I'm gonna start off with a straightforward one, then I'm gonna show you a more interesting. Okay. Let's do an example. Let's say I have a 10-volt battery here. Pass through here. Pass through here. Pass through here. Pass through. And we need some values here. So, let's say this will have, I'll do these, so this will be C1, make this 2 microfarads. This would be C2, 3 microfarads. Actually, yeah. Okay, we're probably gonna get really painful numbers here because I'm just making these up. This would be C, yeah, okay. 3 microfarads, and then these will be, this will be C4, C5, C6, and these will all be equal. They'll all be, let's say, 6 microfarads. Okay. The question is, hey, find CEQ and the total charge of storage. There's a problem here. The problem here is board space. Okay, this is gonna be this is gonna be kind of messy on this stuff here. So part B will be find V and Q in each capacitor. Okay. This one's gonna get really kind of tight. I apologize for this. Okay, when you do these, you always have to draw intermediate steps. If you do not draw the intermediate steps, absolutely nothing is gonna work. Okay, so when you do these things, always ask yourself, what are the obvious things in parallel? What are the obvious things in series? And then redraw the picture. So let's look at this and do it in steps. Is there anything obviously in series or obviously in parallel?
C4, 5, and 6.
Yeah, these right here are in parallel. So let's actually then redraw that picture with all these in parallel. So I'm going to call the parallel combination of this. I'm going to call it the 4, 5, 6 combination. So I'm going to redraw this picture to here. I'm going to make it a lot smaller. This is C1 here. This would be C3. This would be C 4, 5, 6. This is C. What would have to be C 4, 5, 6? They all add. Okay. And so this would have to be C4, C5, C6. So this would all have to be 6. Well, it would be 18. Now, ask yourself the same question again. Is there anything obviously in series or obviously in parallel? Yeah. Why are these obviously in series? No, not for series.
They're connected end to end.
With nothing intervening. So you go directly from one to the next, to the next with nothing intervening. Okay. Why isn't C1 in series with them? What's screwing it up? the battery, right? Because if you look here, if you follow this wire here, oops, you hit a battery, okay, there's something in between. Okay, that's why it's not in series. Whereas these, I go directly from here to here to here, they're in series. And so what's gonna happen here, actually, I'll put a little circle on these ones here, I'll call this parallel. Then I'll put a little circle along here like these, and I'll call this series. And then redraw that picture. So if I redraw the picture, you get C1. You get C2. And then you get this guy here. And this is going to be not that well. This one here, I'll then call C2, 3, 4, 5, 6. Okay, what would be C 2, 3, 4, 5, 6? Yeah, this is going to be reciprocals. So this right here, this is going to be 1 over C 2, 3, 4, 5, 6. This is going to be 1 over C2, it's 1 over C3, plus 1 over C 4, 5, 6. So this is going to be 1 over 3, plus 1 over 3, plus 1 over 18. So this would be what? 2 over 3, plus 1 over 18. 6 here like this. So this would be 7 over 18. Sorry about that. Okay. 1 over C 2, 3, 4, 5, 6. So what is the capacitor then? And I write down 7 over 18.
Microphone.
Okay, can I write down 7 over 18 microfarads? How come?
Since
You have, again, it's gonna be really easy to stop right there and say that's the answer. No, you don't have to flip it. So what this means here is that the C 2, 3, 4, 5, 6 is 18 over 7.
2/3 is about 12. It's not 6, 18.
Oh, that's, yes, okay. I multiplied top and bottom here by 12, by 6, and we got a 12, I don't know what I did. So this is a 13, and so this is a 13. Thank you. Keep me honest. Okay, now that's the same thing again. Is there anything obviously in series or obviously in parallel?
One here are in parallel.
How come?
Their tops and bottoms are.
Yeah, it looks weird, but they're in parallel, right? Because this top here is connected directly to this top. It doesn't matter the fact that the battery's in between. Okay, and this bottom here is connected directly to that bottom over here. Again, it doesn't matter that the battery's in between. If your tops are connected and your bottoms are connected, you're in parallel. So this picture here now goes to this right here. I drew this off to the right. Should I have drawn it off to the left? Yeah, it doesn't matter where you put it. Okay. So it's like here, I could have put it up here, I could have put it down here. It doesn't matter, just as long as it's on this side. Okay, what is that CEQ going to be?
1 plus 2, 3, 4, 5, 6.
Yeah, this is just going to be C1 plus C2, 3, 4, 5, 6. Okay. If I give you one like this on the exam, I would run the numbers to make certain that you get something reasonable. I would not have you working with 18 over 13. But this is, since I just made the numbers off the top of my head, you end up with 18. Okay, so our C1 is what? 2. This is 18 over 13. So this is gonna be what? 26 plus 18 over 13. Or the wonderful, well, 44 over 13. And again, I will work something to make certain you don't get something utterly stupid like that. Yeah. Does that make sense? Okay, so that's our equivalent capacitance here. Good. So what's going to be the total charge stored in our circuit? Battery has a voltage of 10 volts, so this is 10 volts. You know that Q equals CV. So we just work it out. So this is gonna be our Q total. It's gonna be your C, or 44 over 13 times 10, or total charge is gonna be the wonderful 440 over 13. Ooh, part A is done. Now, this is why you need the intermediate pictures, and do not do these without drawing intermediate pictures. You can't do this one easily without making a lot of mistakes without these intermediate pictures. Okay, to do these, you now run all the pictures backwards. You start here, and you're gonna go from here to here, and then from here to here, and from here to here. So let's start. So, where did this fellow come from? That capacitor came from the what? No more, go one step back. That came from the parallel combination of C1 and C2, 3, 4, 5, 6. What's always the same in parallel? Voltage. Okay, so what do I know here? I can automatically say that the voltage on this guy has to be, right? Because the voltage here is 10, so that means there's 10 volts across here. So there's 10 volts across here, and this comes from the parallel combination. Voltages are always the same in parallel. That means that this V1 has to equal this V total has to equal 10. Okay. And then what do we have over here? We know that the sorry about that. We know that the voltage of 2, 3, 4, 5, 6 has to equal the voltage down here. So this also has to equal 10. So what's going to be the charge on our first resistor? Frequently called a capacitor. Yeah, we're just gonna say this is gonna be our C1 V1. This is gonna be 10 times 2. Actually, let's put it in the right order. 2 times 10, so this would be 20 microfarads. Woohoo, that one's out of the mix. Okay, so tell me what the charge then on 2, 3, 4, 5, 6 is gonna be. Sadly, yes. Okay, so this is gonna be C2, 3, 4, 5, 6 times your voltage of 2, 3, 4, 5, 6. And this is gonna be our 18 over 13, 10, or we end up with 180 over 13. What would be the units for that?
Microphone.
That'd be a microcoulomb. Just like down here, this would be a microcoulomb. Okay. Now let's ask the next question. Where does this capacitor here come from? Which one?
Series.
This one comes from the series combination of these resistors and capacitors. Hey, what's the same for capacitors in series? The charge. So if I know that this charge is the wonderful 180 over 13, that means that the charge on each of these also has to be sadly 180 over 13. So I can immediately say that Q2 is 180 over 13. That Q456 is 180 over 13. And that Q3 here, this guy is 180 over 13. Okay. Let's get these two out of the mix. Okay, so tell me what V2 has to be then. Q equals CV. Then V is what we see. This has to be what? This has to be our Q over C. This has to be 180 over 13, all divided by what is our Q3? So the V2 has to be 60 over 13. Ooh, that's something else. We'll put boxes around things that we know. Meaning ones that are all done. Okay, well, then that means that this V3, since it has the same value of capacitance here, is going to be the same thing. So our V3 It's Q3 over C3. So this has to be the same thing. It's going to be the 60 over 15. That makes sense? Okay, tell me what now the voltage is. For 4, 5, 6. Yeah, it's gonna hurt. It's gonna, yeah, it's dumb. Okay, so this is gonna be our Q456 over C456. So this is gonna be the unfortunate 180 over 13 over, where is it? 18. Okay, so this is gonna be 10 over 8, 10 over 13. Okay, where does my buddy C456 come from? The parallel combination of C4, C5, and C6. Hey, what's the same in parallel? Voltage. Always a voltage. So that means that our V4 has to equal V5, has to equal V6, has to equal V4, 5, 6, has to equal 10 over 13. Okay. So tell me what then Q4 is going to be.
Voltage times.
Yeah. It's going to be C4, V4. So this is going to be 3 times this 10 over 13 with 30 over 13. 6. No, this will be, this one is it? Oh, 6. Oh, thank you. So this will be 60 here on microcoulombs. Since all the other capacitors are the same, it's going to be the same thing for all these. So you track those down? Again, they're not hard, but you need those intermediate figures. If you don't have the intermediate figures, good luck with that. Questions with that? Now, here's what I always do, and it drives, I think it drives even my other colleagues nuts when I do this. It only drives us students nuts. I'm going to set up something that looks really stupid, but the reason I'm setting it up to look stupid is not to basically torment you. The reason I'm setting it up is when you set up circuits in a lab, they frequently look like this. So this is all fine drawing a circuit like this, but when you set them up in a lab and you have to track it down, they never look like this. They're all screwed up. And so what I want to do is draw a circuit basically that you'd get often in a lab and then have you work that out. So I just want to repeat this, but now for something. I'm going to draw a circuit diagram of how one would look like in a lab. Okay, don't draw this picture until I check it myself, because I'm just going to kind of draw random stuff, and if you're not careful, you can come up with things that you can't solve. Can't solve easily. Okay, so don't draw this down until I tell you it's possible. Let's say we have a battery here, we have something going up this way. Capacitor here, I'll have one over here. One here. One here. Over to here. One here. That. Wire coming off here. Capacitor. Here. 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 Don't draw this yet. Boom, 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 that's fine. Boom, boom. Boom, okay, that's fine. Okay. Let's give these values here. Okay, so this would be C1, C2, C3, C4, C5, C6, C7, C8. What I want you to do is basically, let's reduce this to one capacitor here. Let me give you some values here. Let's say this is 4. Everything's gonna be in microfarads. Let's see, 6. 6. No, we're not gonna do that. We're gonna do 3 and 3. This is 6. This one. One. Two. Two. Let's find. The equivalent. Again, this is not to torment you, but this is how the circuit's gonna look often when you set them up in the lab. You put wires here, then you have to track things down. Okay, so you do the exact same thing. You always look for obvious series and obvious parallel. So, and then redraw it. So is there anything here obviously in series or anything in here obviously in parallel? Yep. Okay, why isn't C4 in that series combination? I mean, I go from here to here to here. Why aren't these all in series?
Because there's a connection between.
Because of this wire right here. If that wire weren't here, then these three are in series. That wire right here screws it up. This combination here. This is in series. Anything else?
C4 and C5.
C4 and C5 are? These right here. These are in series.
It's in C8 or in.
Are they in parallel?
Their tops and bottoms are.
Yeah, it looks weird, but their tops and bottoms are connected, right? I can go from this top to that top, and I can go from this bottom to that bottom. Their tops and bottoms are connected, even though it looks really stupid. Okay, so this combination here is in parallel. So now the hard part here is going to be redrawing the picture correctly. And this will just take practice. So there's kind of two parts. First of all, just figuring out what is in series and parallel, then redrawing it. And when we redraw it, we're going to make it look good. We're not going to make it look stupid like this. Okay, so now let's make it look proper. So start with the battery here, and then start with the battery, and then look at what happens when you go to the right. Look at what happens when you go to the left, and then when you go to the right. So if I go to the left, what do I run into? I run into this capacitor, and then this combination of the capacitors. Okay. So I have a wire here. I'm going to shift this over a little bit. I have a wire coming off here. I can run into C1 right here, right? I can go here and run right into C1. That's the top right here. Or I can go here and run into this series combination here. So I'll put this here for no good reason. C2, 3. Okay. So let's start with that part here. Now, what happens with those two? If I follow C1 and if I follow C2, 3, what do? Well, they connect together.
Yeah.
Okay. So I'm going to draw these two, then connecting together. Okay. Okay. Now, if I'm here, after they've connected together, what do I run into? C4, 5 combination. Then I'm going to come down here, and then I'm going to put a C4, 5 here. So that now gets to being right here. Now, what does this do? This goes right back to the tail end of the battery. Now, could I have done the following? Could I have drawn it? Let's say I didn't have this. Could I have drawn it like this? And call this C4, 5. Could I have done that? Yeah, I could have done that. Why didn't I? No reason. Okay, that's going off to the left. Now let's go off to the right. If I go off to the right, what do I run into?
C7.
C7. I come over here. I run into C7, so I'm going to put a C7 here. On the other side of C7, what do I run into?
Parallel 6, 8.
Parallel 6, 8. So you're going to come here. I run into the parallel 6, 8 combination. At the bottom of the 6, 8 combination, what do I do?
Comes back to.
Goes right back to the tail end of the battery. And I have here, over here, and like that. So that's how I've now redrawn my picture. That looks all, that's sort of normal. Okay, let's get some values in here. What is C23? These are in series. How do capacitors end in series? Reciprocals. So I have here, I would have that the 1 over C23 equals 1 over C2 plus 1 over C3 equals 1 over 4 plus 1 over 4 equals a half. So this guy here is 2. Tell me about C68. Yeah, these are in parallel. So this is C6 plus I'm sorry, C6 plus C8. And so this is just going to be 6. Tell me about C45. These are reciprocals. So this is 1 over C45, 1 over C4, plus 1 over C5, 1 over 1/2 plus a half. So this is 1. Okay. Now ask yourself the same thing again. What is obviously in series and obviously in parallel?
1, 2, 3 are in series. Or in parallel.
Okay, so these right here, these are parallel. Anything else?
C7, C6 are in series.
These are in series. Now we redraw that combination now. If we redraw it, let's go over here, start with the battery. And you go off to the left. You go off to the left, what do I run into?
C1, 2, 3.
The C1, 2, 3 parallel combination. I'm going to come off here. Here is my C1, 2, 3 parallel combination. At the end of this parallel combination, what do I run into?
4, 5.
The C4, 5. So I'm going to come down here. I draw C4, 5. This side of the C4, 5, what do? I run back to the end of the battery. Okay. Now let's go off to the right. If I go off to the right, what do? Right into the,
Series 6, 7, 8.
yeah, the series combination of these guys. So I run into the C7, 6, 8. Okay, at the tail end of this, what do? I run back into the tail end of the battery. They go back here. Like this. Does that make sense? Hey, let's do this again. Anything obviously in series or obviously in parallel? Well, actually, let's get some numbers here. Tell me about C23. Frequently called C123. This is 2. Yeah, they add. So this guy here is going to be C1 plus C23. So this is going to be 2 and 2. So this is 4. And tell me about C6, 7, 8.
Okay.
Reciprocal there. In this case here, we have 1 over C768. It's 1 over C7. It's 1 over C68. So this is 1 over 6 plus 1 over 6, which is 2 6 or a third. So this guy becomes 3. Okay. Anything obviously in series or obviously in parallel?
1, 2, 3, and 4, 5 are in series.
Yeah, these right here are series. And that's all we have. So let's redraw that picture. So if I redraw that picture here. What is the value for C 1, 2, 3, 4, 5? Yeah, actually, really, what is it? So our, what is our C 4, 5? 1. Could have worked out the numbers in there for. Oh, well. So what happens here? This is going to give us the 1 over C 1, 2, 3, 4, 5. Is 1 over C 1, 2, 3. It's 1 over C 4, 5. It's 1 over 4. It's 1 over 1. So this is going to be 5/4. So tell me about C 1, 2, 3, 4, 5. It is 4/5. Okay. Now, was obviously in series or obviously in parallel?
Parallel, 7, plus 1.
Yeah, this top. Connected to this top. This bottom. It's connected to that bottom. These right here are in parallel. And that gives me this guy. So this is going to be what? This is going to be the C 1, 2, 3, 4, 5 plus C 7, 6, 8. So this is unfortunately 4/5, 5/4 plus where is that? 3. With a common denominator here of
4/5.
what?
It is 4/5.
Oh, it is. I looked over there. Okay, top and bottom by 5 here. So this is gonna this is messy. 19 over 5. Yep. And with that said, perfect end of the class. Okay. Does that make sense? It ain't hard, but it's really, really easy to make a mistake. If you're working on homework with these with a friend, kind of check at each stage. Because if you don't really, these are going to be remarkably unforgiving. If you make a mistake at one little step, then if you go back and trace it back, everything's going to be wrong. Okay, so these are remarkably unforgiving problems. So if you work together with a friend, kind of check at each stage. Have a great day. See you Friday. When's your homework due?
Friday.
Friday.